Okay, so a little bit of detail about how you figure out what your aliases are when you're using a fractional factorial design. Um, let's say you're doing a quarter fraction here. So you have your two defining contrasts, W1 and W2. Well, then you also have the generalized interaction, W1 and W2 as well. Those are all going to be the sources that you need to take into consideration as you consider the effects that become aliased within your model. So using that previous example from before, we had our two defining contrast of ACE negative BCD. And so we had the generalized interaction of ABDE. We remember that's the modular 2 kind of multiplication of terms if we exponentiate terms. All right, so again, if we generalize this, we can kind of think of this in a more not such specific way. So I equal W1 equal W2 equal W1 by W2. So we also have A equal to AI equal to A W1, each of those generating contrast or generalized interaction. Okay, so in our example, we had those equal to I, and as a result, we have A equal to CE. That was our first set of aliased effects. And negative ABCD, notice that's just A by that term, by BDE. These were all reduced exponents by modular 2. Make sure you can see where that comes from. But for example, here, I'll go with the first term. I was going to go with the last term for some reason, but I'll go with the first. When I multiply A times W1, I get A squared CE. A squared modular 2 gives us just CE for this first one. Same idea over here. Okay, so we could do this for a large experiment where our whole set of effects are, we figure out which ones are going to be have important alias terms. So that example dealt specifically with A. We need to generate it for B. We need to also generate it for C, D, E, and then we go on, okay? When you design a fractional factorial, make sure that you want to go through each of these because you want to make sure that you do not alias really important effects within your model, or that those important effects are aliased with things that you can kind of reasonably ignore, like A being aliased with CE. Maybe CE is something you can easily ignore. You can't ignore A though. What you don't want to see is things like a main effect being aliased with an important interaction that you know has significant interpretive value in your model.
Let's see. You still haven't logged on yet.
All right, now that you've seen how difficult generating a fractional factorial design can be, I really like that Gary laid out in the book how you can do this more readily. Because like I said, this is, each time you do it, it's like starting anew, unless you do this every day of your life. Okay, so if you have a 2k minus p design, there's going to be some set of k minus p factors for which the fraction's going to be complete. And you want to choose that easily to be the important factors, the ones you really need to investigate. And you want to do it in a way that is going to facilitate you designing the experiment, not be easy. I was going to say easy at first, but it's never going to be easy, but more readily available what those k minus p factors should be. In fact, there are usually lots of sets of those k minus p factors that would reasonably work. You just got to somehow figure out a set where none of them are alias to your I, your defining contrasts that help you come up with the fractional set. Okay, so in the example previous, where I was equal to ACE, negative BCD, negative ABDE, for example, any set except ACE and BCD will work. If you really need to include ACE and BCD in your set of K minus P factors, then clearly you do not want to use this particular set of defining contrasts. Okay, so Gary calls this included factorial the base factorial. So it will be the case that any other factor will be aliased to some other interaction of the factor in that base factorial. I like the way he uses that because it reminds me of like a basis in linear algebra, right? You can think of it as that generating set, okay? So going back to our example here, I won't read through all the terms again. A and B and C can form a base factorial. So in this case then, D is equal to negative BC and E is equal to AC. So notice D and E come from or can be generated by A and B and C. Okay, again, think about linear algebra. When you find the basis, you can generate every other component of that matrix based upon some linear combination of that basis. Okay, so here A, B, and C can generate the other two main effect terms in the model. Or we could have used A and D and E. Rather than A and B and C, you could have used A and D and E as the base factorial. Then B would be ADE and C would be AE. So see how that works? I really like, I did not learn this way of thinking about it when I first started using fractional factorials back in the day. But I really like the way that our friend Gary lays this out here. I think it's really useful. It's one of the reasons actually I chose this book, because I felt like his way of talking about this was so much better than other textbooks. Okay, so we need to build our base factorial, thinking about what our base is, and then tack on those extra levels based upon the base. So you remember before when we had that huge table and it looked like, well, how do you come up with all those negative ones and ones? And I said, don't worry about this right now. Well, now I'm gonna show you how those terms are realized, okay? So for example, if our base effect, if we're trying to estimate the grand mean, let me say that, begin. We don't want to estimate A, B, or C. So all those terms are negative 1 here. Consequently, if D, we know from the generating set that D is equal to negative BC. That we did in the previous slides. So BC would be negative 1 times negative 1, which gives you positive 1, but negative BC is then negative 1. AC is going to be positive 1. So there we've got we know what the coefficient for D and E is. Notice our final effect, E, because everything else is a negative 1, but E is positive. So notice we have to delineate here what our base factorial is really estimating when we take out the full, the remainder of the K minus P terms. Okay, let's take a look at A. Step through maybe one more set here. A is 1, then negative 1 for B and C. This will be negative 1, this will be negative 1. So we really do estimate A here. But things aren't so pretty once we get to B. Positive 1, negative 1, negative 1. So we get a positive 1, positive 1. Notice how we actually are estimating B, D, and E as our final effect. This is tacking on extra levels. So we have contained, let's look at C. we get D tacked on. When we look at AB, we get D tacked on. D is a common one to be tacked on. D and E, I should say, because they are the terms generated by our base factorial. So make sure you understand where that comes from. But let's talk about the analysis and reflect upon that idea of the base factorial. So we want to analyze a fractional factorial, in particular a 2 to the k minus p, as a complete factorial in the base factors. Okay, and look at this. Our base factors do not match our final effects because we have these other effects tacked on. Okay, but don't forget that you have some aliasing. So suppose you want to analyze our experiment for A, B, and C, and your BC interaction alone looks kind of big. Okay, why is that important? So why is that important? Right here. Remember that D is aliased with ACDE, which is aliased with negative BC, negative ABD. So if we just take the negative of these terms, then we get that these are all aliased with each other. So what we're seeing here with that big BC interaction may just be that D main effect, because the D main effect is the negative of that. So if this BC interaction is large, well, maybe what we're really indicating is that the D main effect is large. And so it gets really hard to know the interpretive meaning, like the actual real life meaning of the effects you estimate in these fractional factorials. Okay. I'm going to stop here, and I think I'm going to do one more video where we just kind of try to wrap this up, because it gets really complicated here towards the end, and I don't want to dive into this after a 12-minute video. So we'll stop here and pick back up, but make sure before you get to this next video in the fractional factorial design sequence, make sure you understand everything that we just went over in the model.